I wanted to go back and talk a little bit about some of the problems I kind of glossed over towards the end of class today. So this is, I believe, it's number 15 on page 264. Yes, 264 in your text. So let's look at this particular problem where it asks us to find a basis for and the dimension of the solution space to this homogeneous system of equations. All right, so let's enter this system of equations in matrix form into our calculator. I'm not going to bother putting in the zeros in here because we know when we reduce that column of zeros, it's still going to stay zeros. So let's go over to matrix, edit. Let's make it a 3 by 3. And the coefficients will be 1, -3, 1, 2, -6, 2, and 3, -9, 3. Now, if you're clever, you'll notice that these last two equations are actually just scalar multiples of the first, but just to go through the process anyway, let's quit out of here. And what I should have done instead of that was just do second entry since it was already typed in there. All right, so there's a reduced row echelon form. So we took the matrix, 1, -3, 1, the 0, 2, -6, 2 with a 0, 3, -9, 3 with a 0, and reduced it to 1, -3, 1, and then zeros everywhere else. Okay, so we know that we can write our solutions. Well, our x2 will be s, our x3 will be t, and our x1 will be 3s minus t. Or if we write it in vector form, we would have x1, x2, x3 is equal to s times 3, 1, 0, and then plus t times -1, 0, 1. We notice that it says that anything in the solution space can be written as a linear combination of these two vectors, and these two vectors are clearly linearly independent. Remember, for a set of two vectors, we can just look to see if one is a scalar multiple of the other. But even easier than that is, notice I have a 1 here and a 0 here. There's no way I can build this 1 from that 0. And likewise, there's a 1 here, there's a 0 here. So there's no way to build this 1 from that 0. So those are definitely linearly independent. So a basis for the solution space will be those two vectors, 3, 1, 0, and -0, 1, 1. Sorry, -1, 0, 1. This is a basis for the solution space. And since there are two vectors in that set, the dimension in this case is 2. Okay. Let's go back up to this problem. Let's see if I can zoom in and out a little bit here so you can actually see it. It asks you to find the coordinate vector of this matrix relative to this basis for M22. I didn't have a chance to go through these, so I'll do the second one here. Leave the first one for you for practice as well as doing the ones in the homework. So again, the way we do this is we want constant times the first, constant times the second, constant times the third, constant times the fourth equals the vector we're interested in. We're trying to solve for those constants. That's why we're setting up this system of linear equations and then making an augmented matrix. Like I mentioned in class, it doesn't really matter how you put the entries in for the very first one, but once you put the entries in for the very first one in a particular order, the other ones need to match the same relative order. Okay. All right, so back over to our calculator here. Let's go to matrix and edit. I want a 4 by 5. I have -1, 1, 0, 0, 2. I've got 1, 1, 0, 0, 0. I've got 0, 0, 1, 0, -1. And I have 0, 0, 0, 1, 3. So again, that was just making our augmented matrix. Let's quit out of here. I want to row reduce it again, so I'll just grab the last entry and hit enter. When we row reduce, we get the identity matrix, which we better see the identity matrix here because we're claiming that this is a basis for M22. So when we put that in columns of a matrix and row reduce, we have to get the identity matrix, and then the solutions are -1, 1, -1, 3. So if I go back up here, let me erase this stuff out of the way just so that we can see some stuff a little bit better. All right, so the coordinate vector, if I call my basis S, the coordinate vector of 2, 0, -1, 3 relative to S is -1, 1, -1, 3. That's how I find the coordinate vector relative to a basis. So again, we're just solving a system of equations. One of the reasons why we want to do this is because we are equating, if you will, maybe corresponding is a better word, but I'll just say it the same way. We are equating this particular vector in the M22 vector space with this vector that's pretty clearly in R4. So we're making basically an identification between elements in M22 and elements in R4. That's one of the reasons why we do this as far as coordinate vectors go. Let's talk about these ideas again. We talked about this in class, but just to go through them again quickly, since I went through them quickly to start with. The first one says, can a set of 6 vectors span P4? Well, the reason why this is yes is because the dimension of P4 is 5. In order to have a spanning set, we have to have at least 5 vectors then, because a spanning set has to have at least as many vectors as what the dimension is. Because remember again, a basis in some regards is a minimal spanning set. It's the smallest possible set of vectors that will do the job to span the vector space. So any spanning set has to have at least 5 vectors. So this one says we have 6, so yes it can, but it certainly doesn't have to. You could make a set of vectors that doesn't span. For example, you could just have the vectors 1, 2, 3, 4, 5, 6. Those are only constants, so I can't possibly I can't possibly span P4. All right, look at the second one. Set of 7 vectors, is that possibly linearly independent in M23? The answer to that one was no. Again, that's because the dimension of M23 is 6. So this tells me, remember again, a basis is the biggest possible linearly independent set. So the biggest possible set that you can make and still be linearly independent is one with 6 elements in it. So this one has 7, so it cannot be linearly independent. Same idea for this third question. Can a basis for R8 have 10 elements? The answer to that is no, because 10 is too many. This has dimension 8. So a set with 10 elements in it can't be linearly independent. Along those same lines, if you were asked, can a basis for P8 have 6 elements? The answer to that would also be no. The dimension of P8 is 9. Remember, it's one more than the n here. So a set with 6 elements isn't big enough. It cannot span. Okay. So this one was too big. It can't be linearly independent. This one's too small. It can't possibly be spanning. Back up here again, for if W is a subspace of V, can the dimension of W be greater than the dimension of V? The answer to that is no. If we let W be a subspace of V, and let, let's say, just call it W1, W2, out to WK, be a basis for W. Then since this is a basis, the dimension of W is K. Also, this set is linearly independent in W, which means that it's also linearly independent in V. Certainly the vectors in W are also vectors in V, so if this is linearly independent in W, if it weren't linearly independent in V, then it wouldn't be linearly independent in W, because I could find the zero vector of V is also the zero vector of W, so I would have the same issue if I had a linear combination that gave me the zero vector. So it's linearly independent in W, so it has to be linearly independent in V. That means either the set is a basis for V, or it can be enlarged to form a basis for V. That's the plus-minus theorem, right? If you have a linearly independent set, you can keep adding vectors to it until you get to the span of the whole vector space. So either since it's linearly independent to start with, it either already is a basis, you can't add anything else, its span is already all of V, or you can find vectors that are in V to throw into it to make it into a basis. Well, in either case, this means that the dimension of V has to be at least K, which was the dimension of W. So if you have, and this just intuitively makes sense, if you have a piece of a vector space, its dimension can't possibly be bigger than the whole vector space. Think about R3. Subspaces look like, well, it could be just the zero vector, which isn't very interesting. They look like lines going through the origin, or they look like planes going through the origin. Or it's the whole space, the whole R3. Lines going through the origin have one dimension, because there's one vector that generates the whole thing. Planes have 2 dimensions because there's 2 vectors that generate the plane. Those are the only types of subspaces that you could have in R3, besides being the whole thing. All right. And then this last question we mentioned at the end of class is just another application of the plus-minus theorem. This is what I just mentioned down at the beginning, at the bottom there. If I have 9 elements in a set, and that set happens to be linearly independent, since the dimension of M43 is 12, I have to add 3 vectors to the set to make a basis for M43. Now, it can't be any old 3 vectors. I have to find vectors that actually do the job to get me to span, but you have to add 3 vectors to form a basis. So hopefully this clears things up a little bit more from class. And be sure to ask me questions if you have any.